This video is about infinite sequences and their limits. We'll start by revising what a simple sequence is. You should have seen that a simple sequence is a finite list of numbers, like this one. It could be something like 1, 3, 5, so on, up to 19, say. And another possible example would be something like 4, 9, 16, perhaps stopping at somewhere like 81. The numbers in the sequence are called the terms of the sequence. So in the second example here, we would say that 4 is the first term and 9 is the second term, and so on. An infinite sequence, like a simple sequence, is a list of numbers, but an infinite sequence goes on forever. So an infinite sequence could be something like 2, 5, 8, and this time the terms just keep on going. Now, if you see 3 dots followed by something, that just means I've left out some of the terms, so that will indicate a finite sequence. But if you see 3 dots and nothing after them, that indicates the terms go on forever, so that's an infinite sequence. We say 2 sequences are the same if all the terms are the same. This means that the sequences must contain the same numbers in the same places. So if I have an infinite sequence like 1, 2, 3, 4, and so on, this is not the same as the sequence that goes 2, 1, 4, 3, and so on. Because even though the sequence has the same numbers, the numbers aren't falling in the same places, so these sequences are not the same. The first 2 sequences I've written here have nice obvious rules for getting the nth term of the sequence. You see, to get the first term in the first sequence, you take 1, multiply by 2, and take away 1. That gives you 1. To get the second term, you take 2, multiply by 2 to give you 4, and take away 1. And this rule will work for every term of the sequence. So we say the nth term is 2n minus 1. Similarly, the nth term of the second sequence here is n plus 1, all squared. The infinite sequence here also has a rule for getting the nth term. Here, we take the number of the term, multiply by 3, and take off 1. So the nth term is 3n minus 1. But not all sequences have a rule for getting the nth term. We can have a sequence that looks really random, like I'd say root 3, minus 5, 99.7, and so on. Now, there's certainly no obvious rule for getting the nth term for the sequence, but it's still a sequence. Now let's look at some notation for sequences. A common way to denote a sequence is to write the nth term in brackets. So for the finite sequence, the first one here, the nth term is 2n minus 1. So we write that in brackets, and we also need to show how many terms the sequence has. So we say the sequence runs from n equals 1, and the last term in the sequence happens to be the 10th term. So we put a 10 up here to show that the last term is the 10th term. Here, for the second sequence, the rule is n plus 1 squared, so we want that all in brackets. And this time, the sequence runs from n equals 1 up to, that's the 8th term, so we put an 8 here. We denote the infinite sequence in a similar way. Again, we put the nth term in brackets, so that's 3n minus 1, all in brackets. And again, we start at the first term, so that's n equals 1. But to show that the sequence goes on forever, we put an infinity here. From now on, we'll just focus on infinite sequences. We're often very interested in what happens to a sequence as n gets large. And there are three particularly interesting things we'll look at. We'll look at, first of all, sequences that tend to infinity. Also, sequences that tend to minus infinity. And finally, sequences that tend to a real limit. First, we'll look at sequences that tend to infinity. We say a sequence tends to infinity if, however large a number I choose, the sequence will eventually get bigger than that number and stay bigger than that number. So if I plot a graph to show you what I mean, you can see a sequence tending to infinity. So what I'll do here is I'll put the values of n on the x-axis, and then I'll plot the value of the nth term of the sequence on the y-axis. So a sequence that tends to infinity looks something like this. Now, the terms here are getting larger and larger and larger, and I've hit the point where I'm going off the page now, but if I could draw a line anywhere parallel to the x-axis, like this one, then for the sequence to tend to infinity, we'd need the terms eventually to go above that and stay above that. It doesn't matter how large a number I choose, these terms must go and stay above that number for the sequence to tend to infinity. Here's an example of a sequence that tends to infinity. We'll have the sequence that's n squared going from n equals 1 to infinity. So that starts off going 1, 4, 9, 16, and so on. So I can plot a graph of the sequence. I won't bother putting in the values for n, I'll just plot the values of the terms of the sequence. So the sequence will look something like this. Now you can see that however large a number I choose, the terms of the sequence will definitely go above and stay above it, because this sequence keeps on increasing and it increases very fast. So this sequence definitely tends to infinity. Now even if a sequence sometimes goes down, it can still tend to infinity. A sequence that looks a bit like this starts off small and goes up for a while, comes back down, and then goes up for a while again, comes down not so far, and carries on going up. Now this sequence does sometimes come down, but it always goes up again, and it will always get above any number I choose, and it will always stay above that as well. So this sequence also tends to infinity, even though it decreases sometimes. Now here's a sequence that doesn't tend to infinity, even though it always gets bigger. We'll start off with the first term of the sequence being 0, and then I'll add on 100, so this is a very big scale here. Put about here. Then I'll add on half of 100, so I'll add on 50. I'll add on half of 50, which is 25. And I'll keep adding on half the previous amount I did. And this sequence does this kind of thing. And the thing is, it never ever gets above 200. So we found a number here that the sequence doesn't go above and stay above. So that must mean the sequence doesn't tend to infinity. And finally, here's an example of a sequence that doesn't tend to infinity, even though it gets really, really big. We'll start off with the first term being 0 again, then 1, then 0, then 2, then 0, then 3, and so on. Now, eventually this sequence will get above any number I choose, but it never stays above because it always goes back to 0. And because it doesn't stay above any number I choose, the sequence doesn't tend to infinity. Now we'll look at sequences that tend to minus infinity. We say a sequence tends to minus infinity if, however large and negative a number I choose, the sequence goes below it and stays below it. So a good example is something like the sequence minus n cubed from n equals 1 to infinity. I can sketch a graph of this. This starts off at minus 1 and then falls really rapidly. So however low a number I choose, the sequence goes below it and stays below it. So this sequence tends to minus infinity. Just because a sequence goes below any number doesn't mean it tends to minus infinity. It has to stay below it. So a sequence like this, which goes minus 1, plus 1, minus 2, plus 2, and so on. Now, even though the terms of this sequence go below any large negative number I choose, they don't stay below, because we always get a positive term again. So this sequence doesn't tend to minus infinity. In fact, this sequence doesn't tend to any limit at all. If a sequence tends to minus infinity, we write it like this. We write xn, arrow, minus infinity, as n tends to infinity, or the limit of xn as n tends to infinity equals minus infinity. And finally, we'll look at sequences that tend to a real limit. We say a sequence tends to a real limit if there's a number, which I'll call L, so that the sequence gets closer and closer to L and stays very close to it. So a sequence tending to L might look something like this. Now, what I mean by getting closer and staying closer to L is however small an interval I choose around L, so let's say I pick this tiny interval, the sequence must eventually get inside that interval and stay inside that interval. It doesn't even matter if the sequence doesn't actually ever hit L. So long as it gets as close as we like to L and stays as close as we like, then that sequence tends to L. Here's an example of a sequence that has a real limit. We'll have the sequence being 1 over n for n equals 1 to infinity. I'll sketch a graph of this. The first term of the sequence is 1, then it goes a half, then it goes a third, and a quarter, and so on. And you can see this sequence gets closer and closer to 0. And if I pick any tiny number, this sequence will eventually get that close to 0, and it will stay that close because it keeps going down. So this sequence has a real limit, and that real limit is 0. I'll now plot a graph of a sequence that tends to real limit 3. So I'll put 3 here, and I'll show you the intervals that I can choose. Now, I can choose a sequence that sometimes goes away from 3, but eventually, you see, it gets trapped in this larger interval, then it gets trapped in this smaller interval. And whatever interval I drew, it would eventually get trapped that close to 3. So even though this sequence seems to go all over the place, it eventually gets as close as we like to 3 and stays that close. So this sequence tends to 3. Now if a sequence tends to a real limit L, we write it like this. We say xn tends to L as n tends to infinity, or the limit of xn equals L as n tends to infinity. If a sequence doesn't tend to a real limit, we say it's divergent. So sequences that tend to infinity and minus infinity are all divergent. But there are some sequences that don't tend to either plus or minus infinity that are still divergent. Here's an example. We'll have this sequence going 0, 1, 2, 1, 0, minus 1, minus 2, minus 1, 0, and then repeating itself like that, and so on. Now this sequence certainly doesn't get closer and stay closer to any real number, so it doesn't have a real limit. But it doesn't go off to plus or minus infinity either. So this sequence is divergent, but doesn't tend to plus or minus infinity. Now this sequence keeps on repeating itself. It will repeat itself forever. A sequence like this is called periodic, and periodic sequences are a good example of divergent sequences.